coffee, water.
Which ones are you going to talk about today? Which topics?
I'm going to talk about some of the 2D and then the defect work for
the
emitters. I'm also going to talk about hydro.
In graphene?
No, actually. In
real hydro?
Yes, in belt semi-metals.
Oh, okay. Good.
Some work with these fine folks here from Amir's group. The student who's working on it, unfortunately, is like really sick today because I was hoping to kind of put her on the spot.
Sure.
But we actually have a couple of papers on it accepted, and everywhere that I've given a seminar, people have like asked me, so can you explain this? And I'm like, don't follow up on it yet. I want to get my Nature paper accepted first. So. No, and I think the large lens scale.
Okay, fine.
I know everyone in this audience is so.
That's the thing about that. Well, let's get going. Today we're lucky in a couple of ways to have Narang here to talk to us. She, of course, is a faculty member that just joined us, and that's the first way. The second is here what she's been doing today. She got her PhD with Harry Atwater in Caltech, and then spent some time with Marin Soljagic at MIT as a postdoc before coming here. She has a remarkable ability to calculate things that most of us can't calculate.
No pressure.
a combination of powerful theory plus the ability to compute it too. She'll be telling us about that today.
Yeah, thank you. Thank you so much for being here. And I'm really excited to share my work on excited state dynamics and quantum interactions. And since this talk is on tape, I will refrain from making too many terrible jokes, both about physics and about staying up late watching the election last night. But I will try and get you excited about our work in calculating quantum interactions and really finding ways that things that are being measured are different from intuition, different from model Hamiltonians, and also how we can predict what people haven't measured yet. So things that involve finite temperature, things that involve driven systems, and things of that nature. Okay, and if there are any questions as we go along, I recognize many of you in the audience. Please just stop me and I can clarify and answer as I go along, because I probably won't remember many slides later what I said. My group works across excited state dynamics and thinking about interaction with molecules. I use the word molecules very generously because we really think about one or maybe two molecules, not really large ensembles of molecules. We think about quantum materials, and this is primarily what I'll talk about here, this being the CIQM seminar, and ultimately how we can leverage some of the tools from quantum information, right? So there are small-scale quantum devices that have become available. Some of them, of course, are smaller than others. So the work from IBM-Q and Rigetti has really shown promise, but they're not error-corrected. These are very noisy devices. But we want to think about how we can leverage a combination of classical and more conventional computing as well as quantum computing in order to predict things about these three areas. Okay, so that is all I will say about quantum information. And I will mostly focus on the quantum materials side of my group. So I'll start out by telling you why we calculate electron-phonon coupling and why, despite the fact that many of the equations that govern electron-phonon coupling that were written a while ago are still hard to compute, why there are processes that are not just at the lowest but also second and third order that become important in understanding the dynamics of quantum materials. I'll tell you about defects both in diamond and in 2D materials. This is primarily to think of defects not as a bug, but as a feature. So going from defects to thinking about these as emitters that could underpin many quantum optical and quantum photonic technologies. As I got into defects, I'll tell you about our work in disorder in quantum materials, and disorder being something that theorists try their best to avoid. It's a really bad word in theory for the most part, but why we are trying to capture disorder explicitly and link with atomic scale imaging of quantum materials. Finally, I'm a very optimistic person, so if time permits, I'll get to our work in merging quantum electrodynamics and electronic structure, the work that my students and postdocs have done in this area. Excited state dynamics. Okay, so how do I think about this problem, right? So people have different approaches to describing non-equilibrium and excited state processes. I think about it diagrammatically, and here's why. When I write down diagrams for different couplings, say it's a photon hitting a material, maybe it excites a plasma, maybe it generates an exciton polariton, maybe it generates a phonon polariton, I can treat different parts of that process at different levels of theory. Right? So I can get my electronic states from a specific level of theory for these types of diagrams. Maybe I can get my electron-phonon matrix elements from a different level of theory, and I can really hybridize different methods using a diagrammatic approach. We've also really tried hard not only to think about excitation, but also excitation under nonlinear conditions or truly non-equilibrium conditions. So what happens when I hit the material with a giant laser as opposed to something that is a weak perturbation? What kinds of interactions would that excite? Thinking about it diagrammatically gives us the flexibility not only to understand at what order the different processes are coming into play, but also to think about at which level of theory we should capture those processes. So when we think about excitonic processes, we should inherently be thinking about a quasi-particle approach. However, when we think about, say, metals, it is sufficient for us, for the most part, not always, to think about a single particle theory. And this is important because they have different computational complexity, and it's important that we merge them in a way that doesn't introduce further artifacts. Of course, once we have carriers, we also want to think about how they're transported, and that's, again, at a different level of theory than explicitly treating the electrons and the phonons of the system. So this is how we think about it diagrammatically, but realistically, this is how we think about it, okay? We write down a bunch of really fun equations. The pleasure of not only writing down equations and writing code that runs on their laptop, but running code that runs on giant computers. In particular, we have a high affinity for computers that have a lot of GPUs on them. And we've developed methods that really scale across large swaths of GPUs, both computational clusters we have in-house, as well as compute time that we leverage from Department of Energy and other supercomputing resources. And this is important because we test some of the things at, say, a small scale for a slightly simplified system, maybe a very coarse mesh. But ultimately, you want to know that in that calculation, it's not something that you're introducing artifacts with a coarse mesh, but actually converges. And to converge some of our calculations, we require things of this nature. So if anyone in the audience is willing to write us a check for one of these, I'm all ears. I keep talking about electron-phonon interactions, and whenever I bring this up, people ask me, well, why is this a challenge to compute, right? You have a giant GPU, or GPUs, and you have an equation. So just do it. Well, there's still a little bit more that we need to think about. And it fundamentally emerges from the fact that electrons and phonons contribute at very different energy scales. So electronic excitations can be on the order of, say, an EV or fraction of an EV when you think about the band gap of most semiconductors. On the other hand, phonons So this is a phonon dispersion, and this is maybe a very idealized electronic dispersion of some magical material. And this is what a one phonon process, and this is a multiple phonon process diagram would look like. Okay, so and phonons really being on the order of MeV, being at a very different energy scale, require us to mesh our problem very differently, right? Because you need to keep for the electron-phonon interactions, the level of detail of both the phonons and of the electrons. So there's a strong energy mismatch. That's the computational side. There's also a fundamental physics side to this as to why this is challenging for us to think about. Most often, people have treated the linear displacement, the Froelich-type Hamiltonian. So this is where in that electron-phonon matrix element, I can keep track of the Ks and the Qs. I can think about the K and K primes, different indices, as well as different phonon indices. And that's important because those types of couplings were previously ignored both in the model Hamiltonian literature as well as to some extent in what is computationally implemented in most codes out there. We made an effort to include not only beyond Froelich-type Hamiltonians, the Biwalla factor, but really to start looking at non-adiabatic phonon contributions. And this gets into a slightly tricky territory from both a theory and experimental standpoint. Let me tell you first where the experimental efforts have encountered this. Experiments at LCLS, at SLAC at Stanford, have seen that really invoking just our conventional understanding of electron-phonon Hamiltonians, even for simple transition metal chalcogenides, is insufficient. What we realized there is because when we think about non-adiabatic phonons, we should really be thinking about the breakdown of the Boron-Oppenheimer approximation. So what you should really be saying is that treating phonons and electrons at totally different scales is insufficient to say that the phonons will respond to the nuclei are, say, different from looking at the electronic cloud, and therefore can be completely separated into two different subsystems, should not always hold. So we're trying to find ways to really treat those types of interactions from a computational standpoint. We got into this by thinking about work in simple 2D heterostructures and including diagrams of this nature, so electron-electron scattering and electron-phonon scattering. And we looked at pretty simple cases, or things that I thought at the time would give us results that would be straightforward to calculate. So looking at a freestanding sheet of graphene, looking at graphite, which is another way of saying many sheets of graphene, but slightly more conventional way of saying that, and also the graphene HBN heterostructure. And something we realized is that the in-plane lifetimes is actually very strongly dependent on out-of-plane interactions. And this is primarily seen in the electron-phonon time, not the electron-electron time. One of the ways you could think about that visually is that if I have a sheet of a 2D material that's like a carpet flopping in the air, and when I lay it out on a hardwood floor, it's essentially held down. So there's some set of soft phonon modes or some set of phonons. We don't have to get into specifics of which phonon modes, but some of them would be more dominant and therefore give us shorter times when you have this floppy sheet rather than when it's laid out on a floor. And actually, that impacts the lifetimes in graphene, particularly in this graphene HBN case. So it's not just that HBN makes graphene chemically inert. It does that. Yes, it keeps the gunk away from graphene, but it also adds this additional component to it of dealing with the phonon modes. And this is something that then got us excited to think about the twisted case. Of course, Pablo and others have given talks at CIQM about this, and we're now trying to think about how the lifetimes change fundamentally as a consequence of the layer with mismatch. Of course, a slight mismatch for us from a theory standpoint and the reason for that is how you would say construct an effective periodic cell for the slightly mismatched case. So if you want to know why we've not been able to trivially do it, that's one of the reasons that 1 degree mismatch is perfectly awful for us to calculate from a theory standpoint. Graphene, HBN, love them, but of course 2D materials come in many, 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 many flavors, right? And one very prominent class of 2D materials is the transition metal dichalcogenides. This is, so let's start with looking at the molybdenum and the tungsten sulfide selenide family. This is a family that has been pretty well characterized. So when you hit it with light, you can get excitations of many flavors. You can get exciton polaritons. You can get kind of bound photonic interactions in these. And there's also an additional role of valley symmetry because of the symmetry in these particular TMDs. And what's exciting about these TMDs is that you can make them, of course, monolayer and form, and you can make mixed layers of these. So you could have a layer that is a molysulfide, another that's a molyselenide. There are different permutation combinations you could do. And in that stacking, you could start to explore some of the questions where I said that the interlayer interaction changes the in-plane behavior and could fundamentally lead to new kinds of physics. So my student Chris Chicorino, who's sitting up here, published a paper on this with me in Nanoletters earlier this year, where we found that there's actually a set of relaxation pathways that were, in particular, the lifetimes for these, far from equilibrium, that were poorly understood. And that, in fact, understanding these is knowing something about the spin-orbit interactions in these materials. Not only knowing something about the spin-orbit interactions, but also self-independently including the spin with the electron. I've been talking about electron phonon times to you for the past few slides. And something that people, an approximation in the field prior to our work was that you can get the electronic states, but not include the spin-orbit coupling in the phonon calculation. So, of course, if you think of, say, the moly or tungsten-based compounds, particularly tungsten, you expect it's heavy, right? Tungsten selenide is heavy, should have pretty high spin-orbit coupling. If it has a bunch of spin-orbit coupling, this should be included. Most people included it in the band structure, but did not include it in their calculation of the electron-phonon coupling. And you would say, OK, well, maybe that's a small correction. Not quite the case. So on this chart here, I'm showing you the effect of spin-orbit coupling. So this is if the Brion, and you looked at the value of the electron orbit coupling, right? So without self-consistently including spin-orbit coupling, you would grossly overestimate the electron. As a consequence of which you would say the electron phonon time is much shorter than what it actually is. You'd also, both qualitatively and quantitatively, predict the mobilities in these materials incorrectly. So we were very excited about this for including it for the monolayer case of these 4 TMDs. And we said, OK, so let's see what happens when you start stacking these, the same material. So now no mixed material, so MOS2 and MOS2. And there are a couple of different options you could have for how you stack them. No twist, but even with the registry, there are a few tricks you can play. Realize that actually in the bilayers, particularly tungsten sulfide and tungsten selenide, is, and I've said, well, loss is an issue, And we started thinking about how can we merge our knowledge of 2D materials, so things of this nature, with our knowledge of metals to come up with a new material, a material that would fundamentally outperform existing photonic materials in the visible, okay? I say the visible because if I go back to this case of graphene here and graphite, and I start doping graphene or graphene HBN, or I start gating it, something that happens as I get further away from Fermi level is that those lifetimes also drop very, very strongly. Okay? So that takes away from the low loss nature of graphene. The challenge was I want it to be really light, I want it to be working in the visible, and I want it to be low loss. Okay? And we predicted a new material, Argentene. We predicted the fact that it's stable. Now, we weren't the first to say you could make metals a monolayer, but most previous work in thinking about metals as monolayers treated them at a gallium level. So essentially said that it's the same as the 3D case, just shrunk down to a 2D. Turns out that actually when you explicitly calculate the material, it adopts a slightly different structure than just taking that 3D case and forcing it down to a 2D case. And this is, again, an argument for why explicitly calculating it rather than using kind of a Jellium or a model calculation would have given you qualitatively and quantitatively different results for the same material. Okay, so this is Argentine. This is 2D silver. I encourage you to adopt the terminology of Argentine, Q-phene, and Orine for the family of 2D noble metals. Okay, so in photonics, I keep saying low loss, right? And yes?
Well, Argentines stick together. I'm used to thinking that how does the stick them go? Because in carbon, you have these very strong carbon-carbon bonds. Then you get the ball and stick model, and that become happy. So you can sort of, but what happens?
So, yeah, so actually we predicted that it would form a stable monolayer, that it would not form islands. And that was actually an important consideration because that if it always formed islands, then it wouldn't truly be a 2D material. We'd essentially be saying you're making small metal clusters which have other issues associated with them. So we predict that it would not only form, but actually there are other barriers you could form to prevent it from rearranging. Right? So now the challenge with Argentine, unlike graphene, is it doesn't have a nice, happy partner like HBN that interacts just enough that it takes away from the soft phonon modes, but not so much that it messes up the electronic properties. Right? I told you it changes the electron-phonon times, but not the electron-electron times. Well, in the case of Argentine, we're looking for that magic substrate that has the same kind of thing where it doesn't take away from the electronic properties of the freestanding layer. Everything we've predicted for this has been for the freestanding case. I will add that in the time that we wrote this paper, and it's now in review, we found out that there was an experiment that came from a group that made 2D gold, so Orine, and they were able to stabilize it on a whole host of substrates using a magical chemical technique to make it. When I was thinking this, I was thinking, oh, somebody's going to do some kind of fancy ALD, or maybe, so this is a theorist's ignorance of how people make materials, but I thought to myself that it'd be a physical technique of some sort that could maybe get to this, and then you would immediately encapsulate it. But they showed that you could actually do this in a kind of a solution-based type thing, and that once you formed the layer, it would be stable and it would just kind of like float off. So I was pretty excited about that, and I hope people can do something similar with Argentine. But that was an excellent question. Okay, so with everything that you say could be low loss, people in photonics have told me that you need photonic figures of merit, and not just a figure of merit. Everyone in photonics has their own figure of merit, so you need all of the figures of merit always. And here we're comparing confinement or propagation. These are my two favorite figures of merit. There are a few others if you think about the ratios of the sheet conductivity, the imaginary and the real parts. But confinement and propagation are easy to think about because you want things to be very confined, because the less confined they are, the more you're getting a situation where you're not coupling in as much. You also want them to propagate for a really long time. So you launch here, and then it keeps going for, I don't know, miles or maybe hundreds of miles. Okay. And we predict that Argentine outperforms not only graphene, but graphene at a couple of different dopings. So this is comparing the fact that graphene, once you start doping it, is no longer that magical low-loss material. In fact, even at kind of a 0.3 or 0.5 EV shift of the EFEMI, whether you gated it, and this is actually assuming that you gate it, not that you explicitly chemically dope it, we see that with Argentine, you can really kind of get the longest propagation lengths, particularly in the visible, where there is this paucity of materials that are simultaneously low loss and have the ability to couple in the visible. All right, so that was the 2D case, okay? 2D, no defects. Let me show you some work that we've done in materials that look 2D-like the valence semimetals, in where they exhibit their interesting transport properties, but are very much 3D materials. This is the work of two of my students, Jennifer Coulter, who is a DOE Computational Science Fellow, and Tina Garcia, who is an NSF Graduate Fellow. Tina, I believe, is in class, and Jenny is not feeling too great today. But if they were here, I promise you, you would hear them, see them, and they would tell you all about this. Okay. But I will try my best to tell you about it as well. Okay, so valence semimetals, we know, come in a couple of different forms, type 1, type 2. There are different ways of classifying them. It really comes down to whether this nice direct cone, you rotate it in 3D, whether it stays straight or it gets a little bit tilted, so whether you're looking at it sideways or looking at it dead on, okay? That is my 10-second view of probably something that people in the field of topology have spent decades studying, okay? So what is interesting to us about valence semimetals, in particular these two here, is that in WP2 and PTSN4, is that they exhibit hydrodynamic flow. And hydrodynamic flow was something that people have studied in graphene. Levitov, Grisha Falkovich, and others have written seminal papers about it. What's interesting is that the same kind of hydrodynamic flow shows up in these very, very 3D materials, right? So this is what the structure of tungsten phosphide looks like. This is not like a nice sheet or 2D material. It's very much a real material. So that's where I got interested, and I said, okay, so you'd expect this with dependent resistivity. But another thing that's surprising to us about hydrodynamics is that most people were using models that were the lifetimes as something that was treated very approximately, and then from there backing out these very complex first, where we think about the microscopics in great detail and see if similar viscosity expressions fall out of it, right? So instead of starting with hydrodynamic picture and imposing it on the material, start with the material picture and see if you recover the hydrodynamics. Does that make sense? Okay. Another thing that's surprising is that most of this happens at lower temperature, which was really surprising to me, because you expect that as you go to lower temperature, quantum physics becomes more and more robust. And in this case, you go to lower temperature and you see very classical physics. That's kind of weird. So we also were inspired by the fact that people had measured in tungsten phosphide, in particular, a strong violation is the Wiedemann-Franz loss, something that relates how electrons and phonons are transported in a material. And the Wiedemann-Franz law is very fundamental. People in thermoelectrics, people in many other fields have thought about this law in great, great detail and thought about how to change different aspects of this very fundamental ratio that you should recover. Okay? So that was interesting to us, not only because people were seeing this in just one material, but now starting to see it in lots of materials. And you see the timestamps in these. These are all kind of 2018 papers. So this is a very exciting, timely kind of thing for us to get into. OK, so we got into it with thinking of tungsten phosphide as our kind of model case. This is a type 2 valence semimetal. It's very low symmetry. It's CMC 2.1 if you think in those terms. And it has this very strong anisotropy, so there's a particular plane that is preferred for transport for this 2D like transport, and everything else is not. That just kind of is ignored. So if you look at these crystals, if you look at like a picture of the whole thing, it kind of has this like needle-like thing, right? So you can tell that there must be one direction in which flow is preferred and the other where it's probably a bad idea. Okay, so we said, let's look at the microscopic picture. Let's look at the lifetime contributions from the different processes and try and recover this hydrodynamic regime. Something we can do in our calculations is look at not only the traditional electron-electron scattering, but also electron-electron scattering that is mediated by a virtual phonon. And we wanted to say, OK, so if we calculate a handful of different types of lifetimes and look at them as a function of temperature, again, we explicitly calculate them as a function of temperature, we should at some point see one particular lifetime that is really, really long or somehow starts to dominate the physics. And that would be indicative of us recovering that hydrodynamic regime. And here, we're looking at different contributions of lifetimes. This is going from high temperature to low temperature. This is going from low lifetime to high lifetimes. And these are the different contributions. And these orange triangles or inverted triangles are what people had experimentally measured, right? So the assumption with hydrodynamics is that there's something that is scattering but is not allowing the momentum to be randomized. That's how there's some kind of collective flow, rather than there being kind of things that resemble typical transport. So we started comparing these lifetimes, and we also started thinking about the small angle scattering, and we realized that actually it's not just the electron-electron scattering that dominates, but also the scattering that is this virtual phonon-mediated electron-electron interaction, so not the typical Coulomb line mediated, but the virtual phonon mediated, that starts to actually become very, very important in order to explain the emergence of a hydrodynamic regime in tungsten phosphide. So we said, OK, so how do those same lifetimes show up in copper, presumably better understood, less messy material? And again, for copper, we start to see contributions from different lifetimes, but we don't see that hydrodynamic signature. OK, so that was for us kind of clear that the lifetimes that we were identifying, were grounded in reality. Well, they're also grounded in reality because we're able to kind of track the experimental outcome here using that one particular set of lifetimes, and you don't see the other contributions from the lifetime track that trend at all. This is something I like, by the way, about temperature-dependent measurements. You can get things right over a small temperature range, but it's really hard to fake getting it right over 2 orders of magnitude. So we're pretty excited about that.
What's the shape of the sample?
So these are needle-like, and they do different kinds of transport measurements. And the lifetime measurements were done by Johannes Guth and Claudia Fessler's group. So.
And how does the surface versus the bulk matter? Because with cyclotron orbits do this kind of thing on the surfaces.
That's right. Yeah. So for these same lifetimes, we don't see that much of a difference between the surface only and the surface and the bulk lifetimes. When they're measuring them, they're seeing a convolution from the two. So it's not something that they're able to completely separate out.
But another. So that they can
That's right. That's right. So what's exciting to us is that there's another very similar looking material, and I'm about to point to these fine gentlemen on the left here from Amir Yacobi's group who are helping us kind of compare tungsten telluride, which could have similar signatures. Actually, we know it to have similar signatures, and it is layered so they can do more kind of precise measurements of comparing just what's happening at the surface versus what's happening in the bulk, and understand the physics a little more. They can also image it. In this case, imaging is hard because it's a crystal rather than a layer. So hurry up, guys. OK, they're giving me the thumbs up. So, yay, awesome. So this is another result that we compared with experiment, and I was very, very happy when I saw this. OK, so the solid line is the theory, and the x's are experiment. This is here looking at the resistivity and looking at the mobility. And there is no fitting parameter here. There is no adjustment, normalization, whatever words you've heard about a fudge factor in the past. None of that. OK. We got the experiments from Johannes Guth. He gave us the data set, and Jenny had the calculations, and they line up. So we understand the quantum transport in tungsten phosphide. And now we're looking to see how general this is for us to understand hydrodynamics in other systems. Another thing that's really cool about this system is that the Fermi surfaces, these type 2 valence semimetals, are pretty kooky. And actually, they have these electron and hole pockets. And we wanted to see if we superimpose the lifetimes that we had, right? Because these plots here are only a subset of the data that we generate. So we actually have the lifetimes generated across the entire Fermi surface, so we can superimpose them on the Fermi surface and see whether there are certain contributions from the hole pocket. By the way, and this isn't just a projector thing. There is actually a layered nature to what happens in the Fermi surfaces of these materials. And I was told not to call them nested because nested Fermi surfaces have a specific connotation, but the electron and the hole pockets actually have this kind of interlaced behavior. OK, so here on top, we're looking at the Fermi surfaces as a function of temperature for tungsten phosphide. The bottom is a more conventional Fermi surface for copper. So you might have seen this, say, in Ashcroft-Mermin or your favorite solid-state class, going from room temperature to going to pretty low temperature. And what you see is that not only do the lifetimes span many orders of magnitude, but also for tungsten phosphide, there are a couple of spots that remain suspiciously looking different than other parts. And this is, again, we wanted to get at the question of what is leading to the violation of the Wiedemann-Franz law, right? The lifetimes tell us half of the picture, but maybe there's something from the Fermi surface that we can figure out, mine out, that tells us why the Wiedemann-Franz law is being violated in these materials. And we also wanted to see how do these contrast with looking at, say, something like copper at low temperatures. So that also required us to then start thinking about how we can extend our own methods, more going from this diagrammatic perspective to something that links with something that more condensed matter theory folks think about, which is this Eliashberg spectral function. And essentially, the idea here is that we can look at the contributions from different phonon modes, and this could allow us to better understand both the optical properties of these materials, as well as understand where the violation of the Wiedemann-Franz law is coming from. So this is now implemented in our method. And by the way, the formalism for this came from P.B. Allen, who wrote a paper about this in 1972, but actually implementing it in a computationally efficient manner, keeping the full electron-phonon matrix element intact is something that took considerably longer than that original formalism. The points of discussion that I want to bring up with looking at the hydrodynamics in particular is that we see these different lifetimes. We see the Coulomb-mediated versus looking at some of the virtual phonon line mediated electron-electron scattering, which really does slow down at low temperatures, particularly as you get below 50 Kelvin. We want to understand if that's what's giving us the violation of the Wiedemann-Franz law. Maybe there's something else. So these are kind of areas that we're looking to understand better. And one of the ways we would be able to understand this better, of course, is if we see this in another material which also exhibits similar physics. That would be kind of a smoking gun for us. I keep mentioning these materials also have interesting optical properties. So this is linking kind of the fact that I love thinking about the photon as well as thinking about hydrodynamics. So the same materials actually have very, very, very high Chi2, right? So they're very low symmetry. And you think about the fact that gallium arsenide has been thought about as an interesting material with nonlinearities, and tantalum arsenide and the whole family of valence semimetals that follow tantalum arsenide could have similarly very, very high Chi2. Of course, you'd want high Chi2 at the same time as low loss, which is non-trivial. But again, we're looking at this class of materials to see if the optical nonlinearities in these valence semimetals could tell us also something about the physics in these materials. With that, I will transition topics a little bit. Everything I've told you about so far has been defect-free, right? So, but we know that things, when you involve defects, tend to have interesting properties, in particular if you can use those defects to become emitters. And this is work in collaboration with two of the CIQM PIs, Dirk Englund and Marco Lonkar, where we're looking to understand color centers in diamond, in particular, thinking about going beyond the NV center to other types of defects, in particular, thinking about the silicon and the germanium. And it's very imaginative. You keep going down the same group, and maybe you think about the tin and the lead vacancy center. So the work for lead vacancy center, order matters. We predicted it, and they measured it. And they measured it exactly where we predicted it. So I was pretty happy about this. This is, again, work done by Chris Ciccarino and one of Dirk's postdocs, Matt Trusheim. So the point with the lead vacancy, in particular, building on the work that people had seen in silicon and germanium vacancy, was that you could get a larger spin-orbit split. This could potentially help improve the spin coherence times. And we predicted the ZPL energy, and that's exactly where the experimental folks measured it, by the way. So what I like about diamond is that people can implant everything in it. So it's a really good test bed for us to think about from a theory standpoint. What is the behavior of the system? It's inherently something that requires us to think about excited states. So the splits and the behavior and the coherence times are all coming from the behavior of the excited state in these materials, not just from the ground state. And this is a really good test bed for us to see where our theories are lacking and where our theories could be potentially improved. In particular, I'll point out a few directions that we're exploring in thinking about defects in diamond. The Jahn-Teller distortions that we need to account for in these materials. So of course, the Jahn-Teller distortion is something that is understood in many other systems. But in the case of defects or color centers in diamond, it actually competes with some of the other effects that you really want. and you don't want to see too much from the Untitled distortion. But of course, when you implant something giant like tin or lead into the material, you expect that it will distort things, right? That's our intuitive, and it turns out to actually be true. In the neutrals, we see that there's the product Jahn-Teller, which is essentially a product of the dynamic Jahn-Teller, which is what you see in the negative color centers. So this is something that is now implemented in our method. Again, work with Chris and with Johannes Flick, one of my postdocs, in linking model Hamiltonians to describe the Jahn-Teller component with our ab initio calculations of what is happening for the ground and excited state splits, and including spin-orbit coupling self-consistently. The hope and dream is that we can screen across the entire periodic table. And I just want to add a word of caution here. This is not as trivial as it sounds, OK? Because as we realized with okay. So, good. I'm glad. I absolutely love that you said that, Bob, because very often people will say, OK, so you understand it for group 4. Why don't you just do it for the entire periodic table? We can implant everything you want, so just tell us what you want. Not so easy, and here's why. Because each other thing that you implant excites new physics in that same diamond lattice. So even though the diamond lattice is very well understood, implanting different defects in it give you different physics each time. And it's like the gift that keeps giving, but also the gift that prevents you from screening across the entire periodic table and saying, here's my magical color center in diamond. This is why I'm going to do it. Okay? So yes, we're working towards screening, but I just want to add that word of caution that this isn't something that we can just take the physics from group 4 and take it across the entire periodic table. There's a reason why different parts of the periodic table are differently categorized. OK, so that was in 3D, right? So the promise of 2D always, yes?
Because there's something that they would really like to do is to get the right color center. I think they're quite flexible about which one that is.
Yeah.
But that it doesn't emit phonons because it's the right environment.
That's right.
2 vacancies,
right.
Not 1. But it has long coherence time with the spin.
Yeah.
Can you say anything about coherence time, or is that some dirt that's added on top of?
So we can address some of the kind of questions in looking at the spin coherence times. For these systems, actually. And we're trying to figure out if there's something more general we can say about which distortion and therefore what kind of spin coherence time. Because that would be more of predicting kind of a larger set of trends rather than saying for this system, this is what we expect.
But yeah, rule of thumb would be good enough.
Yeah, right. Yeah, so we're actually working towards that. So I'm looking at Chris, who's not making eye contact with me now, to say that yes, we should absolutely do this potentially before the experiment can, so that we actually have a predictive component of the work here.
Magic RIE out in
right.
Albuquerque can take one of those.
Yeah.
Whatever it is. Yeah. Good.
So. It's interesting that, so you mentioned the RIE and implanting in a 3D lattice. The promise of 2D is essentially kind of the opposite, which is to say that instead of having to implant something and then find it, you could implant where you want it because all the atoms are on the surface, and then you know where the defect is, and maybe you could do more interesting things like coupling across different defects and all of that good stuff. Right? So with everything that sounds that promising, there's always a catch, but also an opportunity. So I think of defects in 2D materials as truly an opportunity for us to engineer new kinds of emitters, but also something that brings with it many challenges. In part, the environmental interactions. So the fact that anything in the environment that we don't account for typically from a theory standpoint, including things like substrates, encapsulation layers, PMMA, PDMS, or whatever favorite polymer people put accidentally or somehow on these materials. It has something fundamentally to do with the electron phonon times that are measured, and therefore the behavior of these same emitters, right? So these are very challenging for us to calculate. But things that we can more tractably calculate are things like long-range ripples, right? So again, going back to my favorite carpet analogy, this is kind of like a carpet that was poorly laid out on the floor. So there's maybe some crinkles, maybe somebody didn't like actually stretch it all the way out, and it has some long-range ripples. And this is important because that actually changes the lifetimes in the sheet. Even if the ripple is, say, somewhere here, you would say, well, the emitter shouldn't see it. No, it does, and it actually starts to matter that we incorporate those types of effects. There's substrate interactions, and with 2D materials, something that we've noticed in particular with the work in hexagonal boron nitride is that knowing which defect it is actually non-trivial. And I would like to advocate for the fact that not only is it knowing which defect, but also the fact that some of these defects could potentially not be the easy to form point defects that you expect, but could very often be complexes of defects. And this is work that I actually want to talk about a little bit. So hexagonal boron nitride, lots of promise, lots of people said, including Dirk, Igor Aronovich, Greg Foos, Lee Bassett, many others, that it could replace diamond. And it's because it has a wide gap, has a lot of defects, large taxonomy of possible emitters, and you don't want the word taxonomy when you think about emitters. You want there to be one, maybe two, but when you say there's a whole bunch of them, that kind of makes people pretty nervous. So what we said is, how about we start thinking about correlating what is measured for HBN. So identifying which defect it is has been very challenging. Okay, so and I won't try and review all of that work in the next couple of minutes I have, but we said maybe there is some way that you could correlate the optical, morphological, and some electron beam property of the material. And with those three things plus theory combined, you would know everything you wanted to know about this material. Okay, so this is in collaboration with Jen Dion at Stanford. They're able to do CL, PL, and TM all at once, or not, maybe not all at once, but in the same column, okay, on the same sample. So what they do is they measure PL from a specific set of emitters. Then they measure the cathodoluminescence, and something they surprisingly find is that they go back to that same spot, they find PL again. So what that tells us is that whatever the beam is doing, it is not destroying the emitter, which is very surprising, because most often when you look at HBN under an E-beam, it should just disappear, or something bad should happen to it. So we suspect, and this actually adds some more credence to the fact that the same emitter could actually be this very non-equilibrium configuration that's hard to form, but once formed stays there because it's, say, near, so they see these pretty close to grain boundaries and other kinds of defects, and maybe it's somehow stuck. And they're not the only ones to measure things that kind of sound like something beyond just a point defect is happening. Everyone keeps saying they see the best emitters in the crappiest samples that they have, which is always a little bit suspicious to me. And I think it comes from the fact that some of the emitters that are actually being measured are the rarer and not so easy to form ones rather than the more native point defects. So this is, I think, a really kind of cool area where we can merge what we know from material science and defects. I'm sad that Franz isn't here, but things that maybe he would capture in his class, things that we would know from kind of the quantum optics side, and fun imaging to really get an understanding of what's happening in HBN. And of course, whenever they have this, they have strain, and strain moves the ZPL around. Not only does it move it around a little bit, it moves it around by a lot of it, and so they see it at different points, and that's, again, something that has been challenging. So we are predicting the strain maps that hopefully should match up with the strain maps that Jen and her crew are measuring. And to see that if we know which defect it is, we know how it varies with strain, we know how the sidebands vary, we should be able to fingerprint, right? So you should be able to do something similar to the way people do image analysis to figure out who's who. You have a set that is predicted, and maybe the set that's measured, and say this is a combination of two things. So maybe there's a cat and a dog simultaneously in the picture, not just a cat or a dog, and that's why you're seeing these two different kind of features all at once. From a theory standpoint, HBN is challenging. You need to think about how you will include charge stability. The fact that in a truly monolayer material, it's actually hard to think about what it means to have a well-defined epsilon, both in and out of plane. So we have charge correction schemes that have been implemented in our code, especially for 2D materials. And these are being now leveraged for us to think about defects in lots of other 2D materials, not just HBN. I will just briefly touch on this, and then I will promise I will conclude right after this. So working with Jen and realizing that you could do CL, PL, and STEM, we started to say, OK, are there other kinds of atomic imaging that could be linked somewhat consistently with what we predict for 2D materials and defects in 2D materials? And how could that allow us to know something about local disorder? Right? So disorder has been, as I mentioned, a really bad word in theory, but maybe we could turn that around. So this is work in collaboration with one of our co-PIs on our MIRI, John Miao at UCLA. They do this kind of atomic tomography, and they now have a scanning version of it. So they can tell you the atomic positions with less than 10 picometer kind of resolution, right? So they really, really, really precisely know the atomic position. So what we wanted to say is that if we looked at the atomic positions from theory and experiment, the simplest case you could do is just compare those, right? So say I form a defect in theory, and I allow the system to relax, and I get a certain set of atomic coordinates, and they measure a certain set of atomic coordinates. Do those line up? And then from there, say, how do the properties differ if you use atomic coordinates from theory versus experiment? And how does the local disorder created in those that they should be able to see that maybe we don't capture, how would that change the behavior? I'm kind of giving the punchline away, but that's exactly what we see. Okay, so if we can take atomic coordinates from experiment, and we can look for, this is for rhenium in MOS2. They pick rhenium because it's heavy. Anyways, they can do other things with it. And there are a few types of things. They saw rhenium on Mali sites, rhenium with sulfur vacancy. And this is now looking at pristine. So let me explain what's happening here, right? So they have a flake. It has about 2,000 atoms. They give us the atomic coordinates, okay? And the atomic coordinates, by the way, not just in 2D, but also in 3D, which is important because that's where you see that Z variation and the fact that they're long-range ripples and all of that good stuff. What we do is take those atomic coordinates, and so we also first predict for these same systems, same defects, what would you expect as the electronic structure. We unfold the bands to see where exactly you would see the different defect positions. But with the same system, using the experimental atomic coordinates, you see that there's actually a whole bunch of shadow bands, and that you see in the electronic structure a lot of non-equilibrium features show up. And this is because when they experimentally measure this, they see that there's a lot of Z variation. They see there's a lot of local disorder created by a defect. And actually, the system doesn't relax down to what you expect will be the equilibrium configuration once you introduce the defect. So this is an inherent assumption in theory that I introduce a defect or an imperfection, and then the system relaxes. This is a phrase you'll hear over and over in most calculations. There's no reason why it should. It could find some local minimum and stay there. It doesn't have to find the global minimum, and that's exactly what happens. And this is something that we now consistently capture with the work that they are doing on the system. So we hope that this paper that quantifies, not just qualitatively says that there is some impact or disorder on the electronic structure, but actually quantifies it, that both of these papers will be out soon. So I am out of time, but I do want to say one more thing about this same system. We can look at the forces, and we can say something about the fact that what they're measuring is a truly metastable system. And this is exciting to us because there's a lot to be understood by linking electronic structure calculations with atomic scale imaging about metastable and disordered quantum materials. And we have a whole bunch of stuff that's happening on this. So if you're interested, please come talk with me. I will not have time to talk about QED, so I apologize, Nick. This is the work of Nick and Johannes. But I will conclude and say that I told you about our work in 2D materials, van der Waals heterostructures, really using theory to predict things that would be either experimentally hard to deconvolve or hard to measure, and then kind of turning that around and saying that atomic scale measurements actually tell us something fundamentally new about quantum materials that are being measured, and that we can link those to understand new things about systems that we thought we understood like MOS2 with defects in it, which has been pretty well studied, but we are now finding that it's not as well understood as you would expect. I showed you some of our mysteries in hydrodynamics, so quantum materials. Lots to be done still, and my group is actively working on this in future. I'd like to thank funding from CIQM. I mentioned some of our colleagues from the Ab initio Quantum Materials MURI, both John Miao and Dirk Englund. Of course, Jen Dion as a part of our Energy Frontier Research Center that was just funded, and a BES grant with folks at Oak Ridge. They also have a complementary set of imaging techniques, so we're excited to work with them. Thank you for your attention. I'm happy to take any and all questions. And of course, I'm on the 3rd floor of Pierce, so if there's a question you want to come ask me, you can just come knock on my door. That also works. So thank you, Bob, for having me here.
Questions?
No, it was maximally clear. Go ahead, Boris.
Go ahead.
I was wondering about the violation of Whitman-Franz law.
Yes.
Is this something you see specifically to the lifetimes, or is this a band structure effect?
We see it in the lifetimes. We also see it in the transport. So transport is the way it's also been experimentally measured. And that's something that, so yes, you would see that in the lifetimes, but the transport would be the best kind of comparison point with experiment.
I was wondering, so if you look at the transport part, if you do Boltzmann transport, the Lorentz number, the first order is independent of the lifetime, right? It cancels out. So it's, I mean, if you do it just a band structure analysis, you see at low carrier concentration, low temperature, the Whitman-Franz law will violate for any semiconductor. So I wonder if that's what you're seeing, rather than anything intrinsic in the lifetime.
We can talk about that some more, but I don't think that this is purely a band structure effect. So, yeah.
Other questions?
Yeah.
So if you calculate the electron phonon lifetime,
Yeah.
or like on the Fermi surface, that's very interesting for if you compare to superconductors, right?
That's right.
So, I don't know, many people still talk about the electron phonon covering two planes, for example, and there are like variation on the Fermi surface. I can see what.
Yeah. I have stayed away from calculating cuprate semiconductors. Go ahead, sorry, I cut you off. No, I've stayed away from that. It's just it seems like a scary area. But we could teach you our techniques, and if you feel bold enough to calculate, please have at it. So, yeah.
Other questions? Well, if not, let's thank Priya again.